Multiple choice question number 1. We have two charges trying to find the electric field midway between those two charges. Let's make the first one -3 because it says the charge on number 1 is 3 times the charge on number 2. The second one is going to be +1, +1,000, +1,000,000. It doesn't matter as long as it's 1/3 the value of number 1. Now, we're going to find the direction of the electric field midway between caused by the negative. Forget about the positive, pretend it's not there. The field points, because of the red one, toward the negative, and the field caused by the blue one is away from the positive. It's smaller than the red one. It's 1/3 the value of the red one because the charge is 1/3 the value. Because both of these are to the left, the net electric field will be to the left. If the blue one was positive, or if the blue one was to the right, then we would say the net field is still to the left because the red one is bigger. In the end, because they're both to the left, it doesn't really matter how big each of them are. The net field, when you have two of them that are pointing to the left, is toward the left of the page. So B is our answer for that one. Numerical response number 1, there's a scenario here. There's a scenario here on this one. I think it's to answer the next several questions here. We got this inkjet printer like you might have at home where we've generating these ink drops. We're charging these ink drops as they go through the electrode, and then they're going to get deflected by these deflection plates. Like we've said before, when you see a page of information, there's not a great deal of information here, but when you see a scenario like this, we want to skim through it. We're not looking for details necessarily. If we notice something, it might lead us to a strategy. Awesome, make a little note of it. But if you don't notice something, that's okay. We're just skimming through it, and then we look at the question. Right? Now that we know what the question is, once we know what the question is, we can go back and find the relevant information there. So let's do that. We've skimmed it. Let's pretend we've skimmed it at least. And now we read the question. It says, the number of excess electrons given to the oil drop. Look, when we want to find a number of electrons, we always take the total charge and divide it by the charge of 1 electron. So we're not going back and trying to find a whole bunch of miscellaneous information. We're going to go back here and try to find what we need. We need a charge. If we want to find a number of electrons, we need a charge. And the good news is, that charge is right there, right above the question. So we're going to say the number of electrons is the charge, the total charge divided by the charge of 1, or negative 1.51 times 10 to the negative 13 coulombs, divided by negative 1.60 times 10 to the negative 19 coulombs. Let's calculate that. Because they're both negative, I'm just going to drop the negatives. By the way, I told you guys we never sub the sign of a charge into an equation, right? This would be the one exception. Although even this one, we could drop it. We could absolutely drop the sign of a charge in here as well, as long as we did it for both charges. But if you don't want to, it's not a big deal because this isn't really an equation. Technically it is, but not one on our data sheet. I know what you're going to tell me. Should be 10 to the minus 19, right? I didn't notice that I did that, but I did notice my answer was 943, and that would be a small number for a number of electrons. It's possible, but it would be a small number for a number of electrons. So that one jumped out at me as not necessarily that it's wrong, but it jumped out at me as being like, maybe I should go back and check that, especially when I saw all the hands go up there. I believe it was 9.44 times 10 to the 4, isn't it? Or 5, 9.44 times 10 to the 5. Let's just try that again. Yeah, 9.44 times 10 to the 5. So we're going to express that as A, B, C, D. A, B, C, and D. 9445 is our answer there. Multiple choice number 2. Again, same scenario. You don't need to skim it again, although if you want to skim it again, you can. On your test tomorrow, it's going to be paper copies. So what it'll do is, opposed to having this scenario listed with every question, it'll say, here's the scenario, use it to answer the next 2 questions and the next 3 questions. So you're not going to see it 2 or 3 times. That's just the way that I did it here, so that the information would be with you in that question. Here's a deflection plates of 0.1 millimeters apart, and there's a potential difference of 120 volts across. And what's the magnitude of the electric field? I don't think I even need to go back and look at this information for this. This is a uniform electric field between two plates. So we're going to say our uniform producer equation, delta V over delta D, it's 120 volts divided by, I'm going to say 0.100 times 10 to the minus 3. To be honest, I'm not real comfortable with just moving the decimal place over there. When I've got a 0 decimal something, I hate moving the decimal place over. So I usually just replace the milli with a 10 to the minus 3, and then that saves me the bother of moving the decimal place over. Okay, if I have 65.2, I don't seem to have any problem moving the decimal place over. But if I have 0.652, it messes me up for some reason. So this is my strategy. I just replace the milli with 10 to the minus 3. And when I do that, I don't remember what I get. 120 divided by 0.1 times 10 to the minus 3 gives me 1.20 times 10 to the 6, is it? Yeah. 1.20 times 10 to the 6, the answer would be A for that one. That's a pretty straightforward one, right? That's a category 2, but it's on the easier end of category 2. We definitely want to get that one correct, right? Build some equity so that when we get that challenge question, we don't have to stress about it. We can afford to make a mistake on a challenge question if we're getting questions like this correct. Next question, still this inkjet printer, multiple choice number 3. This time, we're looking for magnetic force. Okay, well look, we just found the electric field. I think we found it was 1.20 times 10 to the 6 volts per meter or newtons per coulomb. Let's use my experiencer equation now. The middle equation in that Venn diagram, E is equal to F over Q, or F is equal to Q times E. So it's 1.6 times 10 to the minus 19 times 1.2. No, it's not 1.6. It's 1.51, right? 1.51 times 10 to the minus 13 times 1.2 times 10 to the minus 6, 10 to the positive 6. I think that gives me D, doesn't it? Is that right? 1.81 times 10 to the minus 7. Like 3 questions so far. And what have I had to do with the information? Almost nothing, right? The only thing I've used is this bottom piece of information here. You understand why? Like we're not trying to go through this information in detail and study it in detail and figure out everything before we read the question. Let's read the question and then let's just find what we need. And all we've needed so far is that charge. Now, I think there's another one that goes along with that. Yeah, there is. Multiple choice number 4. This one says, in order to follow the path shown, the direction of the electric field between the charge deflection points must be which way? So it's important to note here that we're talking about a negative charge. Notice I'm not putting LH or RH here because this is not a magnetic field. We're using hand rules for a magnetic field, not for electric field. This is electric field. We know how to deal with the electric fields. It's simpler than the hand rules, right? If it's a positive particle, the force is with the field. If it's a negative particle, the force is against the field. Well, look, this particle was moving to the right, but this particle gets deflected upwards, so the electric force must be upwards on it. If we have a negative particle that experiences an electric force upwards, then that means the electric field must be which way? Downwards, yeah. If it's a positive particle, the force was up, the field would be up. But a negative particle, the force is up, the field would be down. So this one's a little trickier, right? This one's maybe a category 2, but maybe a 2B because you have to recognize first field is opposite to the force, and second of all, you have to realize that, like, okay, because it curves upward, the force is upward. Okay, once you recognize that, we see that the field must be toward the bottom of the page. Notice it doesn't say down, right? It says toward the bottom of the page, right? We've talked about that quite a few times, the frame of reference for us. So A would be my answer for that one. Two conducting spheres have identical surface areas. Sphere A has a charge of 4.5 microcoulombs. B has a charge of negative 2.4 microcoulombs. A and B brought into contact, separated to a distance of 2.5 centimeters. We want to find the force after contact. Be careful here. What some people will do, this is not insanely hard, but there is a two steps to this. We can't just say F is equal to, well, we can say K Q1 Q2 over R squared. That's correct. But the charges are not 4.5 and negative 2.4. Right? What are the charges? Nope, not 4.5 times 10 to the minus 6. We got to add them up and divide by 2, because it says they're brought into momentary contact. So when they brought into contact, they balance, right? Two identical conducting spheres here. When they brought into contact, they balance. I believe that was 1.05, isn't it? That ring a bell? 1.05 microcoulombs. So 8.99 times 10 to the 9 times 1.05 times 10 to the minus 6 times 1.05 times 10 to the minus 6. And then we'll divide that by 0.025 meters. That make sense, you guys? Just be careful, read the question, answer the question, right? This is not an insane question, but we do have to recognize that they touch together. And we know what happens when they touch together. They balance. So let's balance them before we do Coulomb's law there. So let's go 8.99 times 10 to the 9 times 1.05 times 10 to the minus 6 times 1.05 times 10 to the minus 6 again. And let's divide that by 0.025. Don't forget to square that. You get a value of 15.9, 15.85. Careful with your rounding too, right? Some people might say 15.8, just blindly, carelessly. They just say 15.8 because they know they got to round it to 3 digits, and the first 3 digits are 15.8, right? Except we're going to go 15.8, and then look at the 4th digit. It's a 5, so the 8's going to round up. 15.9. 15.9 is our answer there. I like this question. Multiple choice number 5. I really like this question. So we've got a charged particle, positive charged particle going from position M to position N. As the positively charged particle moves from position M to N in a region between oppositely charged parallel plates as illustrated above, as a result of this change in position, what happens? What happens? Well, let's look at a few different factors here, okay? Let's look at electric field. Let's look at the electric field. What do we know about the electric field at position M as compared to N? The field. That's not even part of the question, but let's just look at that for a second, okay? What do we know about the field everywhere between these two plates? Yes, positive particle goes with it, absolutely. What else do we know about the field? What do we know about the strength of the field in different positions? Position M, N, or even over here. It's going to be the same. So the field does not change. The electric field does not change. Agree? Good. Okay, look, if the field doesn't change and the force, look at my experiencer equation, E is equal to F over Q. And F is equal to Q times E. Well, the charge certainly isn't changing. If the field isn't changing, then what does that tell us about the force? Does the force change? Sorry? No. Force can't change, right? Because the field isn't changing. Now, if the force isn't changing, now we're not asked about this, but what about the acceleration? Would the acceleration change? No, because A is equal to F over M, right? If F force isn't changing, then the acceleration wouldn't change. Now, would the speed change? Would the speed change? Yes. Just because we say the acceleration isn't changing doesn't mean it's not accelerating, right? It is accelerating. There is a force. It will accelerate. Is it going to increase or decrease in this case? As the positive particle goes towards negative, the speed is going to increase. Yeah, the speed's going to go up. If the speed goes up, the kinetic energy will go up. If the kinetic energy goes up, then the potential energy will go down. Because the total energy has to remain the same, right? We know a car going down a hill, that's what this is, right? Is a car going down a hill. As a car goes down a hill, the kinetic energy increases and the potential energy decreases. The gravitational field doesn't change as the car goes down the hill. The force of gravity doesn't change as the car goes down the hill. The acceleration doesn't change, but the speed does, the kinetic energy and the potential energy does. So what's our answer here? D, our electric potential energy of the object is decreased. Now, we did more when we went over that than we needed to answer this question, right? But maybe that's helpful to another question down the road sometime, whether it's on our unit test tomorrow or whether it's on our readiness check at the end of the semester. Multiple choice number 6. So we got a thundercloud. You can see the thundercloud has a positive charge on the top, negative charge on the bottom, and then there's a tree there. Don't stand next to a tree in a lightning storm. Lightning likes to take the easiest path, and a tree is the tallest thing, so lightning will often strike trees before it strikes anything else. You're actually better off in the middle of a field than you are right beside a tree. Crouch down, kind of make yourself as small as you can into a ball in a field. Don't stand under a tree. Cows were never known to be the smartest animals in the world, all right? Oh, look, there's lightning. Let's go hang out under the tree. What's the question asked me here? It says, the bottom of a thundercloud usually becomes negatively charged. It can become positive, but usually negative. Before the lightning strikes, the charge on the ground directly beneath the thundercloud will become what? Before the lightning strikes, before charge is transferred, what's going to happen to the ground here? Well, if the top or the bottom of the cloud is negative, then we're going to get a temporary separation of charge here. This is the Earth. Equal number of positives and negatives. When the negative is closest to the Earth, what's it going to do to the positives? Nothing. What's it going to do to the negatives? It's going to repel them away. So the negatives are going to get pushed way down into the Earth. Not all of them, right? But we draw it as if they all do. The negatives get pushed down into the Earth. So the part of the Earth that's nearest the cloud will become positive. Is it positive by induction or positive by conduction? Boy, it's been a while since we did that, eh? Induction, because charge wasn't transferred. Induction, charge wasn't transferred. Now, as soon as lightning strikes, as soon as the electrons come down, then we got conduction, right? But right now, it's still induction before it strikes. So the answer is A, positive by induction. Oh, another one here. Multiple choice number 7. During the downward strike, the charge on the top of the tree becomes, well, we know it's going to be conduction, right? Because charge is transferring now. Now, if negatives hit the tree, then the tree is going to become what? Negative. Yeah. During the strike, the tree will become negative because you just introduced a whole bunch of negatives there, right? If the tree was effectively neutral, we had billions of negative charges, we're going to get a total negative charge. So B is our answer there, negative by conduction. Numeric response number 3. Experiment is performed using an initially neutral metal sphere and a positively charged dome of the Van de Graaff metal sphere, blah, blah, blah. You know, let's pretend we've skimmed it. I'm not going to read through the whole thing. Let's pretend we've skimmed it here. One thing that I noticed, though, here, one thing that did jump out at me, when we did the Van de Graaff generator in class, I told you that the dome of the Van de Graaff generator is negative. This one, for whatever reason, they say is positive. So I'm just going to make a little note of that it's not what I expect it to be. That may or may not be relevant here. Okay, it may not, I can't even remember what the question is, so it may not be relevant, but I'm just making a note of that just in case the charge is relevant. Now, if you don't notice that as you're reading it, that's okay, right? Because we're skimming it. When we read the question, if we need to know whether the charge is positive or negative, we want to go back and find it. We're not going to assume. We're going to go back and find, is the charge negative or positive? See that it is positive here. All right, what's the question asked me here? Oh, the magnitude of the electric force. I don't like that second diagram, actually. We did a question similar to this. Do you remember that? I think it was on a Friday, actually. We've got a tension force right here. I'm going to call that Ft. That's the string. We've got an electric force. It's pushing the metal sphere away from the Van de Graaff generator. And we've got a force of gravity that's pulling that metal sphere down. Now, what they've done in the second diagram is drawn for me a vector diagram. I don't really want the vector diagram. Okay, they're showing me, look, gravity and the electric force combined to give me the tension force. I want to look at it as like this, as a free body diagram. I want to say, look, these are my three forces acting, and because this is suspended, we know that we're in a state of equilibrium. Forces must balance. We know that the X component of the tension must balance the electric force. And we know that the Y component of gravity must balance the gravitational force. We're looking for the electric force. We're looking for this one here. So why don't we just say cosine 78 degrees is equal to the X component over the force of, oh no, we're not going to use cosine. Let's use tan, right? Tan 78 degrees is equal to opposite. Yeah, opposite over adjacent. Fx is equal to Fy, which is the same as gravity, right? What do we need? We didn't read this question in detail. We skimmed it. What do we need here? We need a mass. Let's go find a mass. I didn't see a mass when I was skimming it. That's okay. Let's go find one. There it is. 2.0 times 10 to the negative 5. 2.0 times 10 to the negative 5 times 9.81. That's Fy, force of gravity. Fy is the same thing. Times, divided by tan 78 degrees. Anybody got an answer for that? Yep. Anybody agree with that? Yes? A, B, C, D, so it's going to be 1964. Oh. Does anybody have the value of X? Yeah, I'm asking for the final answer. Consider the 5. Everybody agree with that? Yeah. So we're going to express that as 4175. Make sense? If you hadn't seen something like that before, that's a category 3 for sure. I think it's a category 2 once now that we've seen it. Like we saw it weeks ago, right? Something like this weeks ago. It's still not a trivial category 2. It's not a gimme question by any means. Even having gone over it now twice, not a gimme question, but it's a doable question, I think. What do we got here? It says, what does it say? X or Y? Does it say what the charges are? Or Y is positive, X is, or Z is, doesn't say what it is. And then we can see that the angles are, one angle is bigger than the other. Okay. Which of the following conclusions comparing either the charges present on Y or Z and the masses of Y or Z is supported? Well, hey, what do we know about the force? The forces between the two. What do we know about the forces between the two? If the force that X applies on Y is equal and opposite to the force that Y applies on Z, the forces are equal and opposite, right? Well, then why would one of them deflect more? If one force is, if the forces are the same, why would one deflect more? Mass, yes. Nothing to do with charge, right? Could they be the same charge? They could be. Could one be more charged than the other? Yes. Could the other one be more charged than the first one? Yes. We know nothing about the charge here, at least the magnitude of the charge. If one of them is +1 and the other one is -30, the forces will still be equal and opposite. If one is +1 and the other one is -0.5, the forces will still be equal and opposite. So the deflection doesn't tell us anything about the charges. It just tells us that one of them is heavier than the other. So we're going to say that, look, Z deflects more than Y, so Z must be lighter than Y. Yeah, Y is heavier. We always say the forces are equal and opposite, right? Every single time, even when I try to trick you, the forces are equal and opposite. But the effect of the forces isn't equal and opposite. Heavier things are affected less than lighter things. Another question with this scenario, the nature of the charge on sphere Z. I think we said Y is positive, right? So what do we know about Z? What do we know that Z is not? Positive, because it would repel. It's attracted, right? So what could Z be? Negative? Could be negative, yeah. But positive will attract negative or neutral. So it's going to be D is our answer there, negative or neutral. Multiple choice number 10. We get this ice pick thing here. We have an electric field that points to the left. We want to know what's going to happen to electrons. Look, if there's an electric field to the left, a positive particle would experience a force to the left. Are you sure? Positive. The force is with the field. But we're talking about electrons, so which way are electrons going to experience a force? Opposite to the field, right? Negative particles experience a force opposite to the field. No hand rules here. This is just electric field, electric force. If the electrons are pushed to the right, then they're going to collect down here at X. The electrons charges do have this tendency of collecting at pointy things, but in this case, they collect at the X pointy thing because the field, the force, I should say, is pushing it that way to the right. So my answer for this one is C, X. If I go too fast there, guys, just slow me down, stop me if you need a chance to write something down or to ask a question, okay? Two positively charged spheres are placed on locations A and B as shown below. We got an angle there, we got an electric field here. We want to find the net electric field that's caused by B. So the net electric field caused by B. This is actually, this is kind of a weird electric field question, because normally when we're looking for an electric field caused by something, we're going to use the producer equation, E is equal to KQ over R squared. And that is valid here, but we don't know anything about charge B, right? We don't know what Q is. We do know R, I guess. But you know what we do know? We do know that the field caused by B is going to be upwards, away from B. We know that because the net field is up and to the right. So if the net field is up and to the right, there must be a field that is up and a field that's to the right. The field caused by A must be to the right. The field caused by B must be up. They both must be positive charges. Oh, they tell me they're positive charges. Go figure. Now we want to find the red one here, right? We're allowed to use KQ over R squared. Not very helpful to me. What I'm going to do, I think, for this one is say, look, I'm looking for the Y component of this net field. So let's say sine 71.3 degrees is equal to the Y component over the hypotenuse, 0.47. We're just doing a vector analysis here. This is actually a question where in Physics 20, Physics 20 students could be the math of this, 100%. Now, they would struggle with this question because they wouldn't understand what they needed to solve for, right? The field caused by B was the Y component of that. But if we told them that the Y component of that 0.47 is the field caused by B, like that's a Physics 20 question, right? Just a vector analysis Physics 20 question. 0.47 times 71.3. Let's make sure we're in degree mode. Yeah, so 0.47 times sine 71.3. By the way, I just checked to make sure I'm in degree mode here. You want to do that too tomorrow, right? We're going to clear your calculators tomorrow. So they're going to go back to radian mode. Now I'm going to recommend that you switch it back to degree mode right away. But the first time you do a calculation with an angle, just check it. Just double check to make sure you're in degree mode. 0.445. This is 0.445. The answer would be C for this one. An alpha particle is accelerated from rest. An alpha particle, I'm going to draw attention to that because it's a positive particle, right? Accelerated from rest to a speed of 5.85. In order to give the alpha particle this speed, what's the potential difference required here? This is like a car going down a hill. This is not a magnetic field question. This is not a hand rule question. This is not an F is equal to QVB or MV squared over R. This is not going in a circle. This is an electric field. An alpha particle experiences a force with the field, and it speeds up. This is like a car going down a hill. And when a car goes down a hill, we always say EI equals EF. Now, the car is accelerated from rest to a speed of whatever. The car at the top of the hill is at rest. What kind of energy does the car have at the top of the hill if it's at rest? Just potential energy, except it's QV potential this time, right? Not MGH potential. What kind of energy does the car have at the bottom of the hill? Kinetic, right? Now, we're assuming that there's no potential on the other side, and that is a bit of an assumption, right? But remember, we get to assume the potential is zero wherever we want, right? Makes sense to assume it's zero at the end. Let's solve for this one here. 3.2 times 10 to the minus 19. The alpha particle mass is 6.65. And this final speed is 5.85. Anybody get a value for that to save me the math? I could do it, but save a second. (1.14 times 10 to the negative 15? I don't think so. I think it should be a 10 to the positive something, because look at the exponent here. It doesn't say 10 to the negative d.
Right.
Yeah, but not for an exponent. I'm going to just double check that, okay? A final answer should have a positive exponent. It tells us, right in the question that we should have a positive exponent for my answer there. So let's calculate the right-hand side. 0.5 times 6.65 times 5.85. Let's square that number. Only square the speed though. And now let's divide that by 3.2 times 10 to the minus 19. 3559. Yeah. Okay, that's okay. 355.9. But we're going to go, what, 3.56 times 10 to the 9? 3569. Is that right? Oh, no. Times 10 to the 3, yeah. What am I doing? Oh, yeah, was that ever brutal? Scientific notation, hey? 3.56 times 10 to the 3. Okay. One more question on this one, on this part of it. We want to find the net force on sphere 3 that's caused by 1 and 2. So let's look at the force caused by number 1. Negative and positive. The force caused by the negative is it's attracted toward the negative. We're not saying the field is to the left. We're not saying the field is to the left or the field is to the right. This is a force problem. we're saying the positive charge is attracted toward the negative charge. So the force caused by number 1 is to the left. And we're going to say the force caused by number 2, the positive and positive, it's repelled away from number 2. It's repelled away from number 2. Good? We got to calculate both of those forces. F1, careful here. F1 is KQ1, watch the units there, times Q3 divided by, watch the units here as well, 0.3 meters. 0.3 meters. The distance is 0.3 meters because we have to add 20 centimeters and 10 centimeters, right? What do we get for that? Cole, what do you have for F1? Not for a final answer, Cole, for F1. You got that written down? Times 10 to the, oh, just 0.8. Okay, okay. Good. Thank you. And what's F2 there? Anybody? Anybody want to help them out here? Not just rely on Cole for all the answers here? 1.81. Now, because they're opposite directions, we're gonna say negative 8.8 plus positive 1.8, which gives me a positive 6.9. Shouldn't it be negative? Shouldn't it be to the left? 6.99 to the left. The force on sphere 3. Did you mix those up, Cole? Yeah, the net force on sphere 3, it's caused by 1 and 2. Is the force of 1?
Well, 3 and 2.
Yeah. I think you might have these forces mixed up here. Yeah. I think you gave me the force caused by number 1 for number 2 and 2 for number 1. Yeah. It would make sense that F2 would be a bigger force, right? Because it's closer. And even though the charge is a little bit smaller, the distance matters more because the distance is squared. Yeah, well, not quite. Because if the blue one was bigger, the net force would be 6.99 to the left, right? And that's what made me spot that, right? The fact that it says to the right. Good.